morning, everyone. I will present you a short presentation about integrating Docker containers in the Yocto project. My name is Sandra Tobajas. First off, I would like to ask you all to please be patient as this presentation is entirely in English and English is not my mother tongue. I am currently working as a product engineering consultant at Savoir-Faire Linux in Montreal. In the past couple of years, I have worked on different projects with customers using completely different business and industrial contexts, and some of them came to us saying, "Hello, I have a new board and I would like to embed my application on this new board. Can you help us?" As their application development was out of our scope, my team and I began to think about how we could help them to integrate their application into their new BSP. Many of those projects were built with Yocto, but the system design would have been the same with another build system such as Buildroot. To continue with my little story, we started to figure out what would be the benefits of running containers in embedded systems. Over time, many questions and issues had been raised during our brainstorming, as we are always trying to align the customer's needs with the reality of the production and industrialization of their product. After the brainstorming, we started to experiment some approaches with Yocto. We came up with two approaches that I will describe during this talk. Most of the time, customers come with their own applicative stacks. For example, one of them had a Qt HMI application based on Ubuntu, and the other had a swarm of services acting as a web server, and was based on an Arch Linux distribution. So, the main goal of the containerization is to decouple the application from the base operating system. You won't need to install some specific distribution package the application relies on or a conflicting library that would pollute the Yocto BSP. To achieve that, the interfaces must be specified between the base operating system and the container. These interfaces can be hardware resources such as audio, rendering devices, shared storage volumes, or even network-related resources. Furthermore, this allows the developer teams to focus only on the application and ignore the platform specificities. With a set of defined interfaces I have listed earlier between the container and the host platform, it brings the ability to run the application container either on a developer machine, a continuous integration pipeline, or a production machine. This allows different update cycles regarding the base operating system and the application. Nonetheless, application and operating systems teams must ensure that interfaces are still coherent. Here is a short list of the benefits of running one or multiple containers in embedded system. Running containers provide isolation of the application through namespaces and many other Linux mechanisms. The overhead in terms of memory consumption, size of the image, startup time is also lower than virtual machines. At this point, everything seems to indicate that running container on embedded systems is a clean solution and should be implemented everywhere. However, that would be too good to be true. Integrating a container brings up relevant challenges that apply in the industrial and embedded world, as they have to be addressed during the product design. Some of these challenges will not be detailed in this presentation as they can be a whole separate topic of discussion. So, in this list, some of the challenges are tied to the embedded context and others are tied to product engineering and commercialization context. The first obvious challenge we can think about when talking about embedded systems is the limitation on hardware resources. Sometimes the devices do not always have enough storage capacity, hardware resources, or RAM to run a container based on a full distribution. Even if the containerization has nearly the same performance as an application in its native system, we have to keep in mind that the container is often based in a full distribution system, and this can add some overhead. The traceability and reproducibility of containers is an important challenge too, as the deployment pipeline can sometimes break. And finally, the management of software licenses is another challenge. Complying with license requirements is essential because it minimizes business and legal risks. Yocto has already a mechanism to track and maintain compliance with various open source licensing tools during the lifetime of the product. So the compliance can be done at the operating system level. However, it does not exist for an integrated container into Yocto build system. To continue with my little story with our customers, part of these requirements are quite common. They can be divided into two parts, the target and the build. The target board has often no connectivity and the root file system has to be immutable, set up as read-only file system. Also, the boot chain integrity can be verified to ensure that all the parts of the boot sequence are not corrupted. Here, you can see a simplified system layout with 4 partitions. The root file system is a squashfs image and contains the Docker engine and the Docker images. We consider the data partition as disposable. It means that if a data corruption is detected on this partition, it can be resetted to factory. From the build system, the Docker images are already stored in a registry owned by the customer. To ensure reproducibility of the build system, Yocto must be containerized. Internally, for all the project, we use CQFD, a small wrapper we built to facilitate running Docker commands that maps the current directory in a project-specific Docker container. So, the Yocto build system is containerized, but the Docker image has to be integrated into the root file system during the build time. Indeed, the container engine must be installed in the build environment. Neither Docker nor Podman have their recipes available as native tools in the meta virtualization layer. In our case, the container engine, Podman or Yocto, or Docker, will be installed in the build container. However, a solution such as Docker in Docker or Podman in Docker has to be integrated into the build process as well as Yocto and bring several concerns. As I said earlier, data corruption is a major cause of embedded device failure, and it is a recurring concern among industrials. Actually, setting a read-only root file system is our practice by default when designing a Yocto BSP. Indeed, data corruption can cause unexpected system behavior even if only one bit is flipped. The temporary data that needs to be written by the container engine can be stored in a volatile or non-volatile writable file system. The difference is that the data will be written once again at each boot or not. But this data is still considered as disposable if a corruption is detected. Therefore, some countermeasures can be integrated to detect such corruptions. In the best case scenario, the system can be able to repair itself after detecting such corruption while maintaining file integrity for critical and embedded systems. The boot integrity verification or mirroring critical partitions can be part of these countermeasures. So, in the first two sections, I have explained the context and the challenges related to embedding a container image into a Linux embedded system. Now let's talk about Yocto and how we have integrated this solution into Yocto. I'm convinced that our approach is not the only way to embrace the problem. With that in mind, I will explain the concept and I will show you the implementation details of the meta layer. Two approaches stood out from our brainstorming. The first is to embed a Docker archive in the root file system, and the other is to populate the Docker store into the target file system. To be precise, I will call the Docker store the varlib docker directory. The Docker store contains information such as data from container layers, volumes, builds, networks, and clusters. The meta I have developed gathers all the components needed to build a simple system image. The meta embedded containers layers is available on GitHub. The distribution configuration file is based on Poky, adding the following features: virtualization and systemd in the system. We will have to add some host tools as Docker and Podman. It allows some external binaries that are not native in Yocto to be called inside the recipe through the host tools non-fatal variable. In the image recipe, the container engine is installed in the machine, and the image is a squashfs image with the read-only rootfs image feature. As the root file system is read-only, rootfs postprocess command allows the Docker engine to be writable, updating dynamically the fstab file regarding on the use recipe. Here, update fstab archive function, the varlib docker directory will be bind mounted on a temporary volatile directory. Now, I will focus more on the container archive recipe, precisely which will embed one or multiple archive in the root file system. Several files can be shared in common between the three recipes. The next step is to put everything in common in one class. All the container images I want to install on the target are listed in this manifest file. I have to specify the image name with its registry if there is one, the tag of the container image, and its local name once the image is installed on the target machine. The container archive recipe is divided into three custom steps between the to fetch and the do install task. First, pull all the images along with their tag described in the manifest file. Here, podman is used to pull the container image with the podman pull command. Secondly, tag the container image with their local name described in the manifest file with the podman tag command. Then, save the container images into tar archive files with the podman save command. The storage driver option is overlay here to allow bigger images to be saved. Finally, once we have saved the Docker image into tar archive files, we install them in the root file system. In the installation task, the recipe will install the systemd service that will load and run the Docker images. Considering this approach, Docker or Podman can be used during the build time to pull and save the Docker image into a tar archive. So, during the boot time, the Docker engine will be present in the root file system. So the step will be mount the Docker store in a writable partition in order to run the Docker daemon, start the Docker daemon, load the Docker archives, and finally, run the Docker images. Indeed, one or multiple Docker images can be stored in the root file system and be run at the same time. The Docker store can be bind-mounted in a non-volatile writable file system. The docker load command could be performed only at once at the first boot or when the writable partition is cleaned. After the Docker daemon is started, the container archive systemd service can be started. There are two steps. First, load the tar archive with the docker load command. This is done with the container load script. And then, once the Docker image is loaded in the local Docker registry, it can be started with the container image script. The docker load command can take some time to perform. Just as an example, it can take around 1 minute to load a Docker image of 2 gigs, depending on the machine hardware specifications. Finally, we can see that all the images present in the manifest file have been started and run by Docker. A variant of integrating container archives approach can be set up with Docker Compose. They are the same steps as the ones described for the container archive recipe. It means that all the container images archive files will be embedded in the root file system. However, we have to install additionally the Docker Compose YAML file here and a modified starter script. The systemd service will load the tar archive files and then start the container swarm using Docker Compose up and down commands linked with the embedded Docker Compose YAML configuration file. Furthermore, the Docker Compose YAML file will point to the local names of the container images loaded in the local Docker registry of the target. Here. Now, I will only focus on the approach that populates the Docker store in the root file system. As the first approach, The update fstab image rootfs postprocess command will update the fstab to mount var libdocker as an overlay fs. Then in the container image recipe, the do pull image task will first off check if the Docker daemon is not already up, otherwise kill it. Clean the Docker store to have a fresh start. Start the Docker daemon specifying the controlled Docker store path with the data root option. The Docker store set by default is var libdocker, but we want to control our own fresh clean Docker store. Furthermore, the use storage driver is VFS, as the Docker store will be mounted as an overlay file system on the target. And as a nested file system that offers unified views, such overlay over an overlay FS is not supported by Linux. Then, once the Docker daemon is started, we can pull the Docker images described in the manifest file. And finally, clean the temporary directories as they will be created on the target system, and at the end, kill the Docker daemon. After that, I am able to install the control Docker store in the target root file system. But BitBake will analyze all the files and binaries installed by each recipe during the do package task. For each file located in the package, BitBake wants to link those files to an existing Yocto package or recipe. However, we don't want BitBake to analyze and add all the container-related stuff in the dependencies. So we will skip the QA packaging. We will also trigger the shared libraries resolver to exclude the entire package when scanning for shell libraries. This can be done by using the exclude from shlibs variable. During the boot time, the Docker store has to be mounted as an overlay FS on a writable partition. Then, launch the Docker daemon, and finally, run the container image. As the Docker daemon runs on top of an overlay FS, we have to consider on how the Docker image has been pulled during the build time. The storage driver defined during the build time, here we have defined VFS, will define how the container layer and data are organized during the pooling step in the Docker store repository. Here, the Docker daemon can figure out automatically which storage driver has been used following the layout of the container layers in the Docker store. The container image systemd service only runs the already loaded container image. The boot time is faster with this approach, as we don't need to previously load the Docker archive files. Many container engines exist, but we want one able to deal with the Docker image format. Podman and Docker are able to handle several types of container archives using podman save or docker save commands. As I said earlier, this consideration happened because our build system and process is containerized and we have to face podman in Docker or Docker in Docker problems. Nonetheless, the choice between Docker and podman happens only for the approach integrating Docker archive. Here is a summary with pros and cons of both solutions. Both can work. The main advantage of Podman is that the tool is standalone and rootless, and sudo privileges are not required. But I had issues to run Podman in Docker with a version newer than 1.5.1 in a Docker container. On the other hand, Docker needs sudo privileges and the daemon has to be started before pulling the image. Finally, here is a summary of both approaches: integrating a Docker image archive into the root file system and integrating Docker store in the root file system. The main difference between both is the boot time. In the first approach, you can have the choice between both container engines, Podman and Docker, considering pros and cons I have listed earlier. The Yocto integration is also easier as only tar archive files need to be installed in the root file system. On the other hand, the second solution minimizes the boot time and the amount of writing operation, as the Docker images do not have to be loaded. The integrity of the Docker images are ensured during the boot and runtime. To conclude this presentation, I would like to share the articles I have written on this topic present in the Savoir-Faire Linux this blog. Also, the Melta embedded containers is also available on GitHub. It is a minimal layer and can be improved. The approaches we proposed are not entirely based on Yocto, as we are installing and using Podman or Docker in the build system, and not using them as native tools. It could be possible to integrate them natively in Yocto. The integration of the container license compliance can be another way to improve this approach. Furthermore, our use case is based on container images based on full distributions. The images are stored in an external registry. These customers' requirements have driven our approaches, but I'm still convinced that is not the only way to embed container images into Yocto.